NVIDIA looks like the ultimate overnight success. Its processors power some of the world's most advanced artificial intelligence systems. And on the 29th of October, 2025, NVIDIA became the first public company to close above a market value of $5 trillion. But that number was not revenue, profit, or cash in NVIDIA's bank. It was the stock market's estimate of what the entire company was worth and what it might earn in the future. That future grew from a failed product, a graphics war, a software gamble, a breakthrough neural network, and a $7 billion acquisition. NVIDIA built the hardware, software, and connections needed to make thousands of chips work as one computer. So why did all those pieces suddenly become so valuable? To understand why NVIDIA won the AI boom, we have to begin with the moment it almost disappeared. NVIDIA was founded on the 5th of April, 1993 by Jensen Huang, Chris Malachowski, and Curtis Prim. Their goal was to make chips for 3D games and multimedia. But NVIDIA's first product, the NV1, was built around quadratic surfaces. The emerging industry standard, encouraged by Microsoft's Direct 3D, used triangles. Developers were moving in one direction while NVIDIA had placed its money on another. The company also worked with Sega on technology for a future games console. That project failed. According to reporting based on interviews with Huang and former Sega executive Shoichiro Irimajiri then helped secure a $5 million investment. Huang said the money gave NVIDIA roughly 6 more months to survive. That is an attributed recollection, not an audited countdown. But NVIDIA abandoned its original approach and redirected its engineers toward the new standard. The result was the Riva 128. The company survived, but survival taught NVIDIA a habit that would later define it: abandon the old bet before the market does it for you. NVIDIA launched Rivu 128 in 1997. According to the company, more than 1 million units shipped in its first 4 months. It was the breakthrough NVIDIA needed. In 1998, NVIDIA formed a strategic manufacturing relationship with TSMC. NVIDIA could concentrate on designing increasingly complex processors while outside foundries manufactured them. Then came the 1999 stock market listing and the GeForce 256. NVIDIA marketed it as the world's first GPU. Whether it invented the category is debated, but the name captured a processor handling many graphics calculations at once. Gaming became NVIDIA's commercial engine. Every generation demanded better effects, more memory bandwidth, faster processing, and useful developer tools. Competition forced rapid, repeated improvement. Gaming created the parallel architecture, engineering discipline, and developer relationships that later made AI possible. But a graphics processor still spoke the specialized language of graphics. Scientists could see enormous computing power inside it, yet accessing that power for other work was difficult. The hardware was becoming extraordinary. Outside graphics, however, almost nobody could tell it what to do. In November 2006, NVIDIA introduced CUDA, a parallel computing platform and programming model. Imagine 2 kitchens. A CPU resembles a small group of skilled chefs handling complicated instructions in sequence. A GPU resembles a large team performing thousands of simpler operations together. Neither is best for every job, but parallelism is powerful when one operation must be repeated across an enormous data set. CUDA gave programmers a practical way to direct that power using familiar high-level languages. A GPU could now be used for scientific simulation, image processing, and other general computing, not only drawing pixels for a game. The strategic bet was bigger than software supporting one chip. More NVIDIA hardware could attract more developers. More developers could create more tools and libraries. Those libraries could make the platform useful for more applications, increasing demand for the next generation of hardware. This flywheel was not guaranteed. CUDA adoption took years, and rival approaches remained possible. But NVIDIA had begun turning a graphics component into a programmable platform. What it still needed was a dramatic proof that this platform could change an important field. 6 years later, 3 researchers used 2 gaming cards and gave the industry its answer: In 2012, Alex Krzyzewski, Ilelia Sutskever, and Jeffrey Hinton entered a neural network called AlexNet into the ImageNet competition, which tested whether computer systems could correctly classify millions of labeled images. The researchers trained AlexNet using two NVIDIA GTX 580 graphics cards. Their paper reported a substantially lower error rate than previous approaches. The result made deep neural networks, and GPUs for training them, impossible for researchers to ignore. Neural network training repeatedly performs large numbers of matrix calculations. GPUs can execute much of that work in parallel. Faster experiments allow researchers to test larger models, change them, and try again. AlexNet did not invent neural networks, machine learning, or GPU computing. It combined existing ideas, larger datasets, and programmable graphics hardware in a visible demonstration. It showed that gaming technology could become a serious AI tool. In 2014, NVIDIA researchers published CUDA, a library of optimized building blocks for deep learning. Instead of every team tuning the same calculations, AI frameworks could use reusable GPU-accelerated routines. The pieces were multiplying processors, CUDA, libraries, and frameworks, yet a large organization still had to choose, connect, and configure everything itself. NVIDIA's next move was to stop selling only the engine and start selling the entire machine. On NVIDIA's 23rd birthday, April 5, 2016, Jensen Huang introduced the DGX-1. It combined 8 Tesla P100 accelerators, NVIDIA's NVLink interconnect, storage, networking, deep learning frameworks, CUDA, libraries, and development tools in one integrated system. A chip supplier leaves customers to assemble the rest. A systems company can coordinate the components, test the configuration, and reduce deployment time. For researchers and companies, this reduced integration risk. They did not have to begin with a pile of boards, cables, and incompatible software versions. NVIDIA could sell something much closer to a working AI computer. DGX also let NVIDIA coordinate hardware improvements with software and communication technologies. But AI models continued to grow. 8 accelerators inside one machine would not be enough for the largest training jobs. Customers wanted clusters containing hundreds and eventually thousands of expensive processors. At that scale, raw computing speed is only part of the problem. Each processor must receive data and exchange results quickly. If communication is slow, valuable GPUs spend time waiting instead of calculating. Once thousands of GPUs work together, the most important component may be the thing connecting them. Imagine hiring 1,000 brilliant mathematicians, then allowing them to exchange information through a narrow doorway. Their individual speed would matter less than the bottleneck between them. Large AI systems have a similar problem. Training is divided across many accelerators. Data must move between processes inside a server and between servers across an entire data center. Slow communication leaves costly machines idle. This helps explain NVIDIA's purchase of Mellanox, completed on April 27, 2020. The U.S. regulatory filing records total purchase consideration of $7.134 billion. Mellanox brought expertise in high-performance networking, including InFIN IH-band and Ethernet adapters, switches, and related technology. These products did not replace NVIDIA's NVLink, which connects GPUs within particular systems. They strengthened a different layer, moving information efficiently across servers and data center networks. The deal allowed NVIDIA to coordinate more of the architecture. Compute, interconnect, networking, and software could be designed as parts of one platform rather than isolated products. The financial importance later became unmistakable. In fiscal 2026, NVIDIA reported $31.376 billion in data center networking revenue. Mellanox did not create every NVIDIA networking technology, but its capabilities supported the company's move from individual accelerators toward data center scale computing. By 2022, nearly every part of the machine was in place. Then the world suddenly discovered what it wanted to build with it. On March 22, 2022, NVIDIA announced its Hopper architecture and the H100 accelerator. The chip included a transformer engine designed to accelerate the type of models behind modern generative AI. NVIDIA said H100 entered full production that September, with partner systems beginning to arrive in October. Then, on November 30th, OpenAI released ChatGPT to the public. ChatGPT did not create the data center market. Cloud computing recommendation systems, scientific research, and earlier machine learning applications applications were already driving demand, and there is no basis here for claiming that the original public ChatGPT launch ran exclusively on H100 accelerators. What ChatGPT changed was visibility. Suddenly, millions of people could interact with a powerful generative model. Technology companies saw a new interface for computing. Startups wanted to train competing models, enterprises wanted assistance, search systems, and automation, and cloud providers needed the infrastructure to serve all of them, and training a model requires enormous computing capacity. Operating that model for millions of users, known as inference, requires more capacity again. NVIDIA had a new accelerator, mature programming tools, optimized libraries, integrated servers, and high-speed networking available just as the demand became urgent. This was preparation meeting timing. Customers were not merely comparing chips, they were competing to secure working AI capacity, and NVIDIA could provide more of the complete system than any single specification sheet revealed. The result was not simply faster growth. NVIDIA's financial statements began to look like those of a different company. In fiscal 2016, NVIDIA generated $5.010 billion in revenue and $614 million in net income. 10 fiscal years later, revenue had reached $215.938 billion, more than 43 times higher. Net income had risen to $120.067 billion, roughly 195 times the earlier figure. The center of the business also changed. Data center revenue grew from $2.983 billion in fiscal 2020 to $193.737 billion in fiscal 2026. That is almost 65 times larger. Data center also represented 89.72% of total revenue. Almost $9 in every 10 came from that part of the business. These are realized business results, not stock market forecasts. They help explain why investors stopped treating NVIDIA like a conventional gaming chip company. The transformation was not perfectly smooth. Fiscal 2026 gross margin was 71.1%, down from 75% 1 year earlier. NVIDIA linked the change partly to complex Blackwell systems and a $4.5 billion charge connected with H20 inventory and purchase obligations after new U.S. export licensing requirements. Still, extraordinary revenue and profit explained only what had already happened. Why were customers willing to keep paying NVIDIA rather than switch to another accelerator? NVIDIA's competitive advantage can be understood as 5 connected layers. The first is compute GPS designed for highly parallel work. The second is interconnect, technologies such as NVLink that move data between accelerators within systems. The third is networking, InFIN band, Ethernet, switches, and adapters linking machines across a data center. The fourth is software, CUDA, CUDA-X libraries, QDNN, communication libraries, compilers, and deployment tools. The fifth is adoption, organizations and developers already building on the platform. Changing one chip is easy on a diagram. In a real organization, switching can mean migrating code, replacing tools, retraining staff, validating models, and accepting the risk of delays. Familiar frameworks can support alternative hardware, including AMD and Intel paths, so customers are not literally trapped. But accumulated software and experience create meaningful switching costs. The company's fiscal 2026 filing says more than half of NVIDIA's engineers work on software. That is revealing. The software is not an accessory added to sell silicon. It helps convert new hardware into something developers can use quickly. NVIDIA's strongest product may therefore be reduced time and uncertainty. A customer can buy processors, systems, networking, and software that were designed to work together. Competitors can challenge individual layers. Matching the coordination across all 5 is harder. That system explains NVIDIA's business. It does not, by itself, explain why the stock market valued the company above $5 trillion. Market capitalization is calculated by multiplying a company's share price by the number of shares outstanding. It can rise or fall every trading day. It is not the amount customers paid NVIDIA, and NVIDIA cannot simply spend it. The speed of the revaluation was extraordinary. NVIDIA briefly touched $1 trillion during trading on May 30th, 2023. Although it closed below that threshold, it closed above $3 trillion on June 5th, 2024. 13 days later, it became the world's most valuable listed company at roughly $3.3 trillion. On July 9, 2025, NVIDIA became the first public company to touch $4 trillion. On October 29th that year, it became the first to close above $5 trillion. Those data milestones capture both demonstrated performance and enormous expectations. Investors saw rising revenue, high margins, and a company positioned across the AI computing stack. But the valuation also reflected a belief about the future, that accelerated computing would absorb a growing share of global data center spending, and that NVIDIA would retain a large part of that opportunity. That distinction matters. Revenue records what customers have already bought. A share price also reflects what investors think customers may buy years from now. If AI demand exceeds expectations, the platform can become still more valuable. If spending slows, competitors gain ground, or margins decline, expectations and market value can fall much faster than the installed technology disappears. And the same system that made NVIDIA powerful also concentrates its greatest risks. NVIDIA's fiscal 2026 filing says one direct customer represented 22% of revenue and another represented 14%. The filing does not name them, so their identities cannot be confirmed. Such concentration means changes in a small number of buying relationships can have an outsized effect. NVIDIA is also fabless. It relies on outside foundries, advanced packaging providers, memory suppliers, and assemblers. That model enables scale but makes manufacturing capacity and geopolitics critical constraints. Export controls have already produced a visible cost. New U.S. licensing requirements affecting H20 products contributed to the $4.5 billion charge recorded in fiscal 2026. Competition is rising. NVIDIA itself identifies AMD, Intel, Huawei, and chips designed internally by cloud providers as threats. Google develops TPUs. Amazon Web Services develops Trainium. Alternatives do not need to replace NVIDIA everywhere to reduce prices or win specific workloads. Finally, NVIDIA's customers are spending vast amounts on AI infrastructure. Over time, they must earn sufficient returns on that investment. None of these risks proves NVIDIA will lose its lead. I cannot confirm that outcome, but a valuation built partly on future growth cannot ignore them. So after 33 years, what is NVIDIA really selling, and can anyone reproduce it? NVIDIA's rise was not one invention or one lucky product. It survived the failure of its first strategy, then used gaming to fund repeated advances in parallel computing. CUDA made those processors programmable. AlexNet revealed their importance to deep learning. QDNN made common AI operations easier to reuse. DGX packaged the pieces into complete machines. Mellanox strengthened the network connecting those machines. And Hopper arrived just before generative AI turned computing capacity into one of the world's most urgent technology purchases. The silicon remains essential, but what customers increasingly buy is time. Less time integrating hardware, less time rewriting software, and less time waiting for thousands of processors to communicate. They are also buying lower deployment risk from a platform whose components were designed together. That combination produced extraordinary profit and encouraged investors to price in years of AI demand that is not guaranteed. NVIDIA spent more than 30 years making thousands of chips behave like one computer. The question now is whether its customers can build an alternative before NVIDIA builds the next version. Is NVIDIA's full stack advantage durable, or are the world's biggest technology companies already building the tools that will weaken it?